Welcome to inverse functions and their derivatives. So before we get into actually taking the derivative of an inverse function, let's just do a quick review of inverse functions. So some quick definitions. F is said to be 1-to-1 on the interval I. If no two x values are paired with the same y value. Or in other words, if f of x1 equals f of x2, then that has to mean that x1 equals x2. If they were different, we would have two x values going to the same y value or same function value. So from here, then note that if a function is f is 1-to-1, then if we're given a y value, we know we can trace it back to the only x that gives that. So if we're given a y value, we can trace it back to the only x with f of x equals that y value. So what we can do is we can find an inverse function that does precisely that. So the inverse of f of x, so often denoted f to the negative 1, for f, a 1-to-1 function, is defined so that if f of a is equal to b, then f inverse of b is equal to a, and f inverse is defined on the range of f. So where the domain of f inverse is the range of f. So we get some key tricks here. Essentially, f and f inverse undo each other. So let me give myself some more space quickly. So we can create the following relationship, just sort of in terms of a summary. If we have x and y, if f sends x to y, then f inverse just sends straight back. But we could also define our x's and y's opposite. So if we did the x and y sort of defined based off of f inverse instead of off of f, So if instead we use f inverse as our main function, we can take f inverse would send x to y, and f would send y back to x. So f inverse and f are inverses of each other. We can think of either one as the one starting with x. So one way that we find the inverse is that if we assume that y equals f inverse of x, then that means that f of y is equal to x. So we are going to utilize this relationship when we go to find the derivative of f inverse of x. So again, if we want to find the derivative of an inverse function, let's go ahead again and set y equal to f inverse of x. Then we can go ahead and rearrange this. So we're going to rearrange this so it's in terms of f instead of f inverse. So this becomes f of y is equal to x. Then we can go ahead and differentiate implicitly. So if we take the derivative of both sides with respect to x, we have the derivative with respect to x of f of y is equal to the derivative with respect to x of x. On the left-hand side, we do the derivative with respect to y first. So that becomes f prime of y. And then we would multiply by the derivative of y with respect to x. And on the right, we just get 1. If we then solve for dy dx, we get that dy dx is equal to 1 over f prime of y. And then we can go ahead and plug back in y. So we know we're going to plug back in y equals f inverse of x. And we wind up getting that dy dx is equal to 1 over f prime evaluated at f inverse of x. Or in other words, the derivative with respect to x of f inverse of x is equal to 1 over f prime evaluated at f inverse of x. So for example, let's consider the function f of x equals log base a of x. And let's go ahead and find its derivative using inverse functions. So by definition, recall that if f of x is equal to log base a of x, the inverse of the logarithm is f inverse of x is equal to a to the x. So recall logarithms and exponentials are inverses of each other. And we know we could also rearrange this then, and instead set g of x equal to a to the x, then g inverse of x is our f of x, which is log base a of x. So if I wanted to find the derivative of log base a of x, it's the equivalent of finding the derivative of the inverse of g. So from here, we're going to find the derivative of f of x. So this is just the derivative of g inverse of x. So f prime of x is the derivative of g inverse of x. And we know that that is equal to 1 over the derivative of g evaluated at g inverse of x. Additionally, we know that g of x is a to the x. And so g prime of x was the natural log of a times a to the x. So if we go ahead and plug back in, we have f prime of x is equal to 1 over the natural log of a times a to the g inverse of x. And then g inverse of x was log base a of x. So if we plug that back in, we have f prime of x is equal to 1 over the natural log of a times a raised to the log base a of x. Now again, if we take the exponential a to the x and log base a of x, those are inverses of each other. A to the log base a of x is actually just x. So we wind up getting that this is 1 over x times the natural log of a, or the natural log of a, times x. So what we get then, in summary, is the derivative with respect to x of log base a of x is 1 over the natural log of a times x. So that is the derivative of just this, any log base a of x, as opposed to just the natural log of x.